So now that we've talked about RxJava and Project Reactor and a bit more about reactive streams, let's talk about how Java's reactive streams implementations can be mapped onto the reactive programming principles that we talked about when we were discussing the Java Completable Future framework. And we'll see how these map to the abstractions that are exposed or defined by the manifesto for reactive programming. So if you recall, the reactive manifesto talks about 4 key principles: responsive, resilient, elastic, and message-driven. And let's start by taking a look first at responsive. So if you recall, responsive was really about trying to give very low latency and very predictable response times for observers of events that occur in a reactive stream or reactive environment. And the idea is not to block anything unduly. And to do that, you have to avoid blocking calling code or caller code. And remember, the reason for doing this is because when you block, you tend to underutilize processor cores, which impedes the ability to leverage inherent parallelism. It can also complicate program structure, and so on and so forth. And the way this is done in RxJava, or Project Reactor for that matter, is to use operators that are defined on reactive streams. And these include things like subscribe on, publish on, and observe on. And it turns out that the different frameworks have slightly different groupings of method names, but for our purposes, we'll be focusing on RxJava. And so we'll be talking about observe on and publish on. And these can be used to avoid blocking caller code. And there's this funny little visualization here on the right, which says a RxJava, or something that involves the use of reactive streams, can represent anything as a data stream that can be created on any thread functionally and transformed and consumed by everyone on any thread. So it's a little whimsical, but it gets the point across. Something else you can do is you can avoid having to change threads if you don't want to incur the costs of synchronization, context switching, and memory and cache management. So this can help to make things have lower overhead while still being able to leverage asynchronous processing and asynchronous programming. Once again, the operators that are defined in RxJava and Project Reactor, like subscribe on, publish on, and observe on, give you this fine-grained control over mapping events to threads. So that was the responsiveness principle. Let's talk now about resilience. So if you recall, resilience is all about avoiding partial failure. If something goes wrong, only the asynchronous operation that had failures will either be shut down or rerun or provided with some default value. The entire program will not come crashing down. And the whole purpose of this, of course, is to make your programs more resilient to failures, especially partial failures. And the way we do this is by having exception handling operators that will decouple error processing from normal operations. And this is actually quite a bit like the exception handling mechanisms that are defined in Java Completable Futures that we talked about. Note that these reactive streams are localized to a single process, not a cluster. So we're just talking about making sure that a process doesn't come crashing down rather than a group of processes that are working together in concert in a cluster. The next principle that we'll talk about is elasticity. And of course, that alludes to the principle of being able to auto scale. So as the workload goes up, your system can respond gracefully by allowing more resources, in this case, more cores, to be brought to bear to make the programs run as efficiently and with the highest level of throughput, performance, and scalability as possible. The way that that's done in both RxJava and Project Reactor is by having a pool of threads that can be used to execute asynchronous computations. And you can see here that RxJava, for example, has a whole slew of different types of threads and or thread pools, like the computation, the thread pool, which is used for CPU-bound jobs, the I/O thread pool, which is used for blocking I/O tasks, and then several other ones as well. Project Reactor also contains schedulers. That's where the thread pools are defined, these things called schedulers. And they also support a bunch of different thread pool models. We won't really focus on them, but if you come back next semester, you can learn more about that. And then the Fourth and final principle is message driven, which means we're going to be sending things in a way that will be decoupled and isolated and capable of being able to be location transparent or location unaware. Remember, this is a bit more of an implementation detail than the other three principles. And the way that this happens under the hood is that all the methods that you see with RxJava and Project Reactor, all those operators we just talked about, those are actually defined internally by passing messages back and forth between different kinds of thread pools or other types of executor environments. And there's all kinds of ways to do this. You normally don't really see the messaging. It's an implementation detail, but under the hood, there's lots of messaging that's taking place. So that's the end of the discussion that shows how we can map the Java reactive streams and the implementation artifacts therein defined by RxJava and Project Reactor onto those four key reactive programming principles that are defined and explained and motivated in the Reactive Manifesto.